Okay, so we're going to get started on chapter 9, which is centers of gravity and centroids. This is going to be the first of 2 handouts for module number 8. And we're going to get started here. And the sections that they're referencing are from this handout that is a PDF also in the learning plan. So I tried to kind of pull these things out, kind of be that guided notes type of thing so that we can just add to what's here. But first of all, the idea or the concept of center of gravity is where we can find the point where we can concentrate the total load of a body. Okay, we've approached this before when we looked at distributed loads. So if you have an evenly distributed load, for instance, if I have a beam, okay, and that beam is homogeneous. Homogeneous means that it's made out of the same material and has the same cross section for its entire length. So for instance, if I have an I-beam, all right, and it's that same I-beam shape all the way along, it's the same material for the full 6 feet. And if I would take a chunk of it 5 feet long or 1 foot long, and I would weigh it and it would be 5 pounds, then that would mean that the total weight would be 5 pounds times 6 feet, right? So the total weight would be 30 pounds. But in actuality, that weight is being distributed evenly over the length of that beam. But to deal with it easier in a static sense, I want to concentrate that full load at what would be the geometric center here. Okay, we use this with distributed loads, and really you can use the weight of something as long as it's a homogeneous body, and you can distribute it over the whole thing, but you can simplify it by concentrating it at its geometric center. So when we do that, we're taking, if you would, the center of that part, and we're concentrating the total weight, called the center of gravity for that particular piece. We see us do this with any body that has weight. We'll go to kind of its center, its centroid, and we're going to show the weight of something going down or pointing down to the center of the earth. Okay. Now, a centroid of a plane body is very easy to find. So it's going to be when we have, for instance, a circle or a square or a rectangle, we can easily find what the center of a plane area is going to be. So in the appendix section, which is also part of a PDF that you're given in our learning plan. So if we go back to the learning plan, you'll notice that we have the chapter 9 PDF, which is the chapter itself, but then we also have the appendix, okay? And at the beginning of the appendix, you're gonna see that there is a chart, and this is going to be the areas and centroids of simple shapes, okay? So here you'll notice we have a square, a triangle, circle, a semicircle, and then a parabolic spandrel that's there. So over on the right-hand columns, you're going to notice that there is a column for area. Then there's a column for where the X bar would be. The X bar is going to be the horizontal dimension for the centroid. So the centroid is in the middle, for instance, of this rectangle or square. And that X bar is the distance from the left-hand side to the centroid. So it's going to be the horizontal distance. It's going to be half of whatever the base dimension would be. And then you'll notice that the Y bar, which would be from, in this case, the bottom to the centroid in the Y or the vertical dimension, would be half of what our height would be. You guys know this. Rectangle, centers of rectangles, center of triangles. We all kind of know these dimensions, but if you need to reference them, they're here for you. So both area and where their centroid is located. Okay, so that's going to be the first chart in our appendix. So I'm going to kind of put this over to the side because we'll reference the appendix later. So that's the centroid of a plane area. So those are easy, and we've come across those, you know, through the years. And we can also we can find centroids by inspection. So if we look at figure 9.6 on page 83 in this handout, centroids by inspection are going to be when we see a symmetrical part, meaning there is an axis for which we have a mirror image on either side. Now, when we have, for instance, like a triangle, as we see here, there is one axis of symmetry, and that's going to be down the middle through the point, and we can see that it's a mirror image on either side of that axis of symmetry. But when we have a circle, for instance, we have 2 axes of symmetry. And each one of those axes where they intersect is going to be their centroid. So if there's two axes of symmetry, then their intersection becomes the centroid. And you'll notice that very same thing with a rectangle or a square happens as well. Okay. So, so if you recognize an axis of symmetry, it becomes kind of a shortcut for us because we know somewhere along that line is where our centroid is going to be. And if we find another one and they intersect, then that is where the location is going to be for our centroid. Okay. So turning the page. What we're going to be focusing on here is going to be finding the centroids of composite areas. Okay, centroids of composite areas. Now, a centroid of a composite area, or what a composite area is when we have a shape that can be broken into simple shapes. Okay, so a composite can take a number of different forms. We're going to be doing example 1, and the composite that we have here, just to give us an idea, is we have this shape that kind of looks like a house that's standing on its side, but then we've got a hole in the middle. So what we end up having is we can break this into multiple simple shapes, but the one shape is a composite of those simple shapes. Okay, so we'll be solving for where the centroid is there. But before we do, there's a couple equations I want to kind of show you that we're going to be finding come in handy for doing problems like this. So first of all, when we want to find this, not only the centroid, but of a composite, but we need to find what the total area is of a composite to help us get there. So you'll notice that the summation of the area is going to be adding up each one of the individual areas of the simple shapes. So we'll have an area 1, an area 2, area 3, however many simple shapes that there are. Now, positives in front of those areas mean that the areas are additive. If there's a negative, that means that there would be a negative space. Like if I take material away, for instance, like a hole or a cutout of some sort, then I would actually have a negative area and it would subtract from my total. Okay. So in the example we're going to do, there is in fact a hole, and we'll see how that works. The next one is going to be when I want to find my X bar. My X bar is going to be the horizontal distance, or the distance away from the Y axis that my centroid is for the composite. So I'm going to find, and I'm going to multiply together the area of shape number 1 and its distance in the X direction from the reference axis for that simple shape. That's going to be X1, plus the area 2 times its X2, plus area 3 times its X3 dimension, and so on for however many composite or simple shapes that we have. And then we're going to sum those. So this is going to be the summation of the areas times the x's. And then we're going to divide that by the total area. Okay. And then you're going to notice that we do that also in the y direction. So now we take that same area number 1, but this time we're going to multiply it by its distance from the reference axis to the centroid of that simple shape. And so it's going to be a y1. So then the a2 times its y2 and the a3 times its y3, and so on. So we'll sum those up, and then we're going to divide by the total area again. And that's going to give us then the dimensions of the x bar and the y bar from the reference axis. And we'll see what a reference axis is in just a moment. So these 3 equations right here, we're going to see come up again in this process. So we're going to mimic the process by going through example 9.1 that starts on page 183 at the very, very bottom. Okay. So on the bottom of page 183, right down here, it says we want to find the centroid of the composite area shown in figure 9.9, which is right up here. Yes.
We could do this programming.
You did. Yep.
Excel.
Yes. So Christian is asking, and there might be some other people in here who had me for computer programming. We did a computer program that calculated the centroid for this problem. You're absolutely right. Yes. It does look familiar. Yes. And if you've had me, and see, the thing is right now, if some of you had, which some of you would have, some of you had Phil for computer programming because you would have had it last year. And then some of you had me. So I'm like, I can't pull it out right now because some of you will have it and some of you won't. So like next year, the whole group will have had me for computer programming. But anyway, but by design, we did a computer program that we could calculate these centroids. So you're right, it does sound familiar, and that's exactly where we did it from. So I'm glad you remembered. I'm glad you remembered. So so this is going to be the shape that we're going to be looking at. So you're going to notice that our circle here is going to be a hole. It's going to be, it says that it's a hole. So that means when we find the area, it's going to be a negative area that's going to subtract out. Okay. But the rest of it is a solid shape. Okay. They have gone ahead and they have determined the simple shapes, and that's going to be one of the things that we do here. So it's actually step number 2. The first step is going to be identifying your reference axis, and your reference axis is just where you say, this is where my X and my Y are going to be for this shape. On the problem, they identified that for us. So you're going to notice in this figure, they have an X and a Y axis. So that means that's where all of our dimensions are going to come from. When you have your problems, you are going to have the X and Y axis identified for you. So you have to use that X and Y axis in then the calculations for the X bar and the Y bar. Okay. So ours is going to come from, if you would, the intersection of that lower left-hand corner. Once we have our reference axis identified, then we identify our simple shapes. So they've identified the rectangle as shape number 1, the whole circle as shape number 2, and then the triangle that's on the end here is going to be shape number 3. Okay. So that's our first 2 steps here. The next step then is to identify any axes of symmetry. Now in this problem, there is one. Okay. And you'll notice that it goes like through the tip of our triangle and through the center of our hole. Okay. And you're going to notice that as we look at these dimensions here, this total distance is 6 inches, and it's 3 inches on either side of that axis. Now, what we're going to be expecting then is that our centroid is going to be falling on that axis of symmetry. Okay. And we'll kind of see that happen. So, so sometimes if you have the freedom, if you would, to identify your own reference axis, you want to set up the reference axis on an axis of symmetry, because then it kind of helps you out with some of the numbers and the calculations. So, so that's that. So we identified an axis of symmetry, and we're seeing our whole part together. So what we want to find is, for this composite shape, where is its center? Okay. So how far up is it? We're expecting it to be along this axis of symmetry. So the Y bar should be 3 inches. Okay. Should be. And then we want to know how far over in this direction is it going to be. Okay. So the next step, as we turn the page, you're going to notice that it says, now what we're going to do is we're going to draw each shape in regard to the reference axis. Okay. So shape number 1 is our rectangle. So you're going to notice that here is our reference axis, our Y and our X. And now we want to position this shape exactly on the reference axis. So you'll notice that this shares the lower left-hand corner with our axis. Okay, this is shape number 1. Once we have that drawn, the next thing we're going to do is we're going to identify and dimension the centroid of the individual shape. So from our original diagram here, and we're only focusing on shape number 1, we know that from that lower left-hand corner, this is 7 inches to the right, and this is 6 inches up, right? So we're going to dimension this as 6 inches and this as 7 inches, okay? So now, using those dimensions, we want to identify the centroid of this individual shape. So we know that it's going to be halfway over, so about 3.5, and about halfway up, 3 inches up, right? So I'm going to draw a little crosshairs here. That's going to be my C1, my center number 1. And now I want to dimension it from the reference axis. I know that C1 is going to be 3 inches up from the bottom. And I know that it's going to be to the right 3.5 inches, right? Now, to identify their direction, I need to identify an X1 and a Y1. So it's going to be the X dimension to the centroid for shape number 1 and the Y dimension to the centroid for shape number 1. Okay, so basically it's whichever dimension is in that direction. So for instance, my 3-inch dimension is going in the vertical direction. This is going to be my Y1. It's also a lot of times stated the distance from the x-axis is going to be your Y value. And then my other dimension, my 3.5, this is going to be my X1. And you can kind of look at it, it's a horizontal dimension, or it's the horizontal dimension and it's the distance from the y-axis to the centroid. Okay. So as we go down here, you're going to notice that we want to gather the following information. So our X1 is going to be 3.5 inches and our Y1 is going to be 3 inches. We also need our area. Our area we know is going to be base times height. We know the base to be 7 inches and we know our height to be 6 inches. So our area is going to be 42 inches squared. So I'm just going to put this as A1. Okay. So these are the 3 pieces of information that we need for each one of our shapes. And the reason we need this information is because if we go back to our previous page, we need our area and we need our X dimension and our Y dimension so we can then fill this in. Okay. Questions so far? All right. Okay. Turn the page. So now we're going to do that very same thing for our next shape. Our next shape is our hole. Remember, we're removing the material here. Now, as far as the size, we have to go back to our original diagram, and up here, it says the hole has a radius of 2 inches, a radius of 2 inches. So I'm going to fill in the area right away. So using that 2 inches, what is the area of a circle? And if you don't remember, that's okay. We can go back to our appendix, right? And we know that the area is pi d squared divided by 4, or isn't it pi r squared, right? Yeah, so we could use we don't need to use the diameter because we're given the radius. So we can say pi r squared. So pi times 2 inches squared. So our area, number 2, tell me my number. Do we know? Yep, 12.56 inches squared. Make sure you put the right units in. Now, this is going to get a negative in front of it, okay? A negative in front of it. And that's because we're removing material, okay? We're removing a material. This is a hole. So we're taking material away, so it has to be a negative. And then we're going to do the same thing for the X2 and the Y2. We're going to find the centroid of our hole, which is right here, C2, right at the center of that circle. And then now our distance is going to come from the reference axis. So I'll highlight that again. These distances have to come from the reference axis that's identified. So for our first one, okay, it's going to be this distance right here. This is going to be our X1. It's going to be a horizontal distance. And from the original diagram, it's 3 inches to the right. And then I might as well grab that dimension right away. It's 3 inches up. So this is going to be 3 inches. And this is going to be 3 inches. So my Y2 is going to be my vertical. And my X2 is going to be that horizontal distance. So we can just say 3 inches, 3 inches. So we've got our area. negative 12.56 inches squared. And we've got our X and our Y values from the reference axis. All right, we've got one more shape. Go ahead and fill this one in. Okay, go ahead and fill this one in. If you need the area of a triangle, put it right here. Remember, we want our distances to come from the reference axis. This is Y, this is X. So for the triangle, you should get an area of 9 inches squared. So the base here is going to be 6 inches and the height is going to be 3, right? And then we divide that by 2. So 18 inches squared divided by 2 is 9 inches squared. The X3 distance is going to come from the Y-axis all the way to, so the horizontal dimension to the centroid. So it's 7 inches to the base of that triangle. And then it's going to be the height divided by 3, or 1/3 times the height. So if the height is 3 inches, divide that by 3, it's going to be 1 inches from the bottom, or 1 inch from the bottom. So it's going to be 7 plus 1 is 8 inches for X3. And then we have Y3 equaling 3 again. Okay. So the reminder at the bottom here just says, remember, all of your X's and Y's for each shape 1 through 3 are always distances from the reference axis that you set back in step number 1. Okay, or was given to you as part of the problem. Okay. Any questions so far? Okay. So as we turn, we're now going to fill in our table. Okay, so for shape number 1, we're going to fill in the area. We're going to fill in its corresponding X, so that would be X1. We're going to multiply A times X. Then we're going to put in its Y, and we're going to do A times Y. So let's go back to shape number 1. Shape number 1 was the rectangle. So the area was 42 inches squared. So I'm gonna go back over here. It's gonna be 42. Now, I have inches squared at the top of our column, so I'm not gonna put the units in the cells, okay? Because they're at the top of the column. So that's 42. My X1, 3.5. Now I'm gonna multiply my X1 times my A1. So I take 42 times 3.5 and I get 147 inches cubed at the top. Then I'm gonna go back and I'm gonna get my Y dimension. My Y dimension was 3. This is gonna be 3 inches times, and I'm gonna multiply area 42 times 3. And that's gonna be 39. No, that's not right. 42 times 3, it's 126.
Pretty sure that was mine.
All right, so now you want to do that same thing for shape number 2 and shape number 3. So I'll let you fill that in and we can compare. Don't forget for shape number 2, that's a negative value. So once we have these filled in, you're going to notice that we have summations at the bottom here for some of them, but not all. And the reason for that is if we go back to the 3 equations that we're going to use, we're going to sum the column that is the total area. Then we're going to sum the column that we have the A times the X's. And then we're going to sum the column where we have the A times the Y's. Okay, so go ahead and fill in my little clouds. You might have done that already. How many, Christian, you had it, James, you had it with, oh, you had it, yeah, that's right. And Kiefer, you had it too, right, with me? Yeah. Yeah, see, there's a reason for this stuff.
I think we were really doing the long way first, like doing all this kind of like, and then it was talking about how to put that into just Excel.
Yeah.
I dread the day when I fully understand that year ratio. we have to.
Oh, it's coming.
Uh-oh.
Next
Don't
year.
let it-
So-
What was that?
so,
Yes, that was good. That was good. He had a rocket spreadsheet that he used for it. It was one of the projects that you guys could do by your own.
Oh, hobby.
All right. Everybody get the same answers that I have here? I didn't do mine twice. I did it just once. Here's my okay, so now what we're gonna do is we're gonna use the equations from earlier. X bar is equal to the summation of the A times the X's divided by the total A's. So we're gonna use this number right here, the 181.3, and now we have to put our units in, inches cubed. Because it's inches squared times inches, so it's inches cubed. So make sure you put your units in there. And then we're going to divide by the total area. This is 38.43 inches squared because it's area. So that means when we cancel our units, 2 of these inches at the bottom are gonna cancel just 2 in the inches cubed. So there's still inches left, which is exactly what we want, because we have X bars, so it's a distance, so we need that to be inches. So what do we get for our X?
717.
Yeah, 4.72 inches. 4.72 inches, good. And then now we're gonna do the same thing for our Y. We're gonna go to that column where we had the A times the Y's. We're gonna take the sum at the bottom there. So 115.32 inches cubed, put your units in, divided by the summation of the area. So that was 38.43 inches squared. So the inches squared cancels out 2 of them on the top. We left with inches. And did you get 3? Yes, by design. And we were expecting that, right? We knew along that axis of symmetry, which was 3 inches up from the x-axis in that y direction, our y bar is going to be 3 from that reference axis. So now the last step is to draw me a diagram of your answer, okay? So we've got our reference axis here, right? Our x and our y. I kind of drew a simplified version of. Now, in perspective, we know the center of our hole was at 3 inches over, right? And we also know that this radius was 2 inches, right? So that means to the end here, that would be 5 inches. So our centroid is less than 5 inches in the x direction. So our overall centroid is going to be somewhere within the radius of that circle, but to the right of its center. And then this is going to be our 4.72 inches. Should have done it the opposite way. This way, this way. This is going to be our X bar. And then we're going to have our Y bar is equal to 3 inches. There we go. So that just lets me know that you know and understand what your numbers meant that you calculated, and that they're coming from the reference axis that we were referencing the entire time. Okay. How'd that go? Kind of fun.
I think this is so hard to understand.
Well, you've come a long way. You've come a long way. If we recognize an area, an axis of symmetry, do we have to show our work for it? No, no. I wanted to show you here, for instance, that it comes out, right? It comes out, but you're right. If you recognize an axis of symmetry, you do not need to show your work. Okay, because it would come right off of there. Good. All right, any questions on that process-wise? All right, cool. Let's turn the page. Let's turn the page. Let's do another example. Example 9.2. Example 9.2. This is on page 185 in our handout. We're going to use that very same process, but different shape. So in this case, we've got a cross-section of a model of an arched dam, as shown. Determine the centroid of the cross-sectional area. So what we have here is down here is the bottom. Okay. You'll notice that our y-axis is coming down the side here. So our reference for this composite kind of goes through the middle there, and then our x-axis is at the bottom going to the right. Okay. We've got this like angled surface. We've got another, it would be a rectangle, right? We kind of see a triangle and a rectangle there. And then we've got this tall rectangle. So we've got 3 shapes in this case for our composite. And we want to find where the centroid is of that entire shape. All right. So first things first, we have to draw ours. Okay. So what I did down here is, you'll notice that it says first things we want to identify our reference axis, which they gave it to us in our problem. I just highlighted it in my handout here. And then we want to identify each one of the simple shapes. So just going to kind of peek at. So what they did for theirs is they identified shape number 1 as being the big, tall rectangle. Shape number 2 is the shorter rectangle on the left-hand side of that y-axis, and then shape number 3 is the triangle. Okay. So let's go ahead and draw each one of our individual shapes here. So this is going to be our place for shape number 1, and that's going to be our tall rectangle right here. Okay. And I'm always going to highlight the reference axis. I can't emphasize enough. You always want to show that reference axis each time we do one of our parts. And then here's going to be my centroid number 1. And given the information, this is 450 millimeters tall and it's 90 millimeters wide. So that means from our reference axis, my X1 is going to be half of 90, which is 45 millimeters, right? And then from my x-axis up is going to be my y bar, or my y1, I should say y1, not y bar for this part, but y1 for our problem. It's going to be half of 450, which is going to be 225 millimeters. So our X1 is 45 millimeters and our Y1 is 225 millimeters. And then our area is going to be base times height. And we know that that's going to be 90 millimeters times 450 millimeters. Okay. Now they use scientific notation, or the to the 10 to the powers of 10. So they have it as, and this is a personal preference. They have it as 40.5 40.5, here, hold on. 40.5 times 10 to the third, and that would be millimeters squared is going to be the area. So make sure you get that with 90 times 450. Yeah. So it's 40,500 millimeters squared, or 40.5 times 10 to the third. You could leave it as the zeros if you wanted to. You don't have to put it in that notation, but you're going to notice in an example they do, and it just kind of does make it a little bit easier. Well, they keep everything in millimeters so that they're consistent.
But we did change.
What was that?
We did change units.
If you, I mean, yeah, you could, but they kept it all in millimeters. Okay, so now we want to do our next shape. Our next shape is going to be the short rectangle that's on the left-hand side of the y-axis, okay? So our short rectangle goes here, right? Our centroid, this is going to be center number 2. Okay. Now the distance over, since it's giving us a distance of 180 for the total bottom, we know that the right-hand side is 90, so that means that this is also going to be 90 wide. Okay. So we know this distance is 90 millimeters. Okay. So that means that our C2 is going to be in the X direction. Okay. This is going to be our X2 dimension. This is going to be 45 millimeters. Now, when we write it over here on the right, notice that it's in the negative X direction. So we have to say that X2 is equal to negative 45 millimeters because it's on the left-hand side of the Y-axis. And then we're going to have a Y2. Y2 is going to be half the distance up. And it lets us know on our illustration that the distance up is 60 millimeters. Okay. Oh, no. The distance up is 60, the total height, so the centroid is 30, I'm sorry, 30, so our Y2 is 30 millimeters, sorry, Christian.
Don't worry, I'm a little bit behind in the writing, so I'm fine.
Okay, because I know you use pen. So if anybody needs to, I know some of you may not have the handouts here printed out, so I'll let you catch up. And then we're gonna do our area. Okay, so that's gonna be base times height. So that's gonna be 90 millimeters times 60 millimeters, which is the total height, right? So from here to here is 60. So our A2 is gonna be 5.4 times 10 to the third. 5.4 times 10 to the third millimeters squared. Questions so far? Kind of starting to see the pattern. And for those, yeah, who had me for computer programming, I don't think we did this specific problem, but same process, right? For the figuring them out.
I might get that program out.
They just screenshot the program and it gave the numbers correct. Does that count?
I'm sorry, say that again.
I'm saying like if we use the program in Excel, I get the correct answers in it. And I just submit that instead of math.
Well, I've already submitted that assignment before.
So William, is that negative because the X, it's because the X is on the left-hand side of the Y axis. It's pointing in this direction. Does that make sense, William? If we were on like this one up here, the X1 was on the right-hand side on that positive side of the Y axis. This is a positive X1, but this one is a negative because we're moving to the left of the Y axis. Does that answer that? Should the area be negative? No, the area is not negative because we didn't remove area. We didn't remove anything away. It's going to be a positive area to add, but the placement of its the placement of its centroid is on the left-hand side of the Y axis. That's why it's negative. Yeah. Good. Any other questions? That was good. I'm glad you asked that. Okay, so we've got one more shape. We've got our triangle, right? We've got our triangle. So we're going to draw that now. Here's our reference axis again. It's on the left-hand side. So our triangle is going to look like this on that left-hand side, right? We know that it doesn't start until the top of that rectangle that we just drew, which was 60 millimeters high. And then our centroid here is going to be something kind of like that. So this is going to be C3. Now for this, our width is the 90, right? 90 millimeters wide. So because this is from this side, the high side, this is going to be a distance of 90 millimeters divided by 3. Okay. And that's going to be my X distance. This is going to be my X3. My X3. Now my X3 is going to the left again of that Y axis. So this is going to be a negative 30 millimeters. Now from the bottom of our triangle, this is also going to be, if this height, do we know how high that is? We do. The height is 60 millimeters. So, let get this, I'm gonna pull it this way. This is 60. 60 millimeters. So that means that this distance from the bottom of our triangle to the top is going to be 60 millimeters divided by 3. So it's 1/3 the distance of the height. So if I take 60 plus 20, right? 60 plus 20, then my Y3 distance. So my Y3 is going to be all the way from down here all the way here. This is my Y3. Does that make sense? Trying to get it in here. I need more room. I always write too big. 60 millimeters there. So my Y3 distance is this. So this is going to be 80 millimeters. It's 60 plus 20. And then we need to do our area yet. Our area is going to be base times height divided by 2. So our base is 90. Our height is 60. And I'm going to divide by 2. So it looks like we get, and I'm gonna kind of write it down here. 2.7 times 10 to the third millimeters squared. Okay. And notice everything is coming from that reference axis. It has to. You can't switch that, you know, as you move along. Once we have all of these values, area, X and Y for each one of our shapes, which now we do, we now get to fill in our table. Okay, fill in our table. So, so go ahead to that next step and fill in the cells for the area for shape 1, the X for shape 1, the A times the X you're going to calculate, then your Y, and then your A times your Y. So I'm going to do that next. And then just verify that you get the same numbers. And then once you have those filled in and you have your totals at the bottom, you can go ahead and solve for the X bar and the Y bar. There you go. It's hard to tell where people are at. Everybody caught up to where I am? And then your last step is going to be to draw the X bar and the Y bar. Now, in this case, it's gonna go, that Y bar is gonna go way up, right? And it's gonna be over just a little bit in relationship. So I don't know, maybe here-ish, right? Is gonna be our centroid. And our Y bar would be the 195.3 millimeters. And then our X bar is going to be to the right. It's a positive value. So that means that it's going to be on the right-hand side of the Y. So this is going to be our 30.8 millimeters, and this is X bar. And then you could draw the whole shape if you wanted to. Boink, something like that. But it's just to recognize exactly where that centroid is, so you understand on this, in relationship to that reference axis, up and over, in this case, both up and then onto the right. Okay, so this feels like a good place to maybe take a little bit of a break. We've done two pretty long problems, and then we'll do another problem when we come back. So why don't we take I don't know, I'm looking at the time, maybe a break until 1:45. Okay, so a little bit over 10 minutes, 12 minutes.